Hello. We have some notes that I posted online, and let me get my little pen highlighter here. Woo, so it's purple. Had some notes that I posted online for you guys to check out. Had the PlayPosit video that used one of the Hewitt Druitt videos, but people were having a little bit of trouble with it, so wanted to go through and actually talk about the content of these notes and go through some of the nuances rather than just assuming that that you got it all figured out yourself. So first off, we did have this diagram. It was in the other video, the Hewitt Druitt, labeling the different parts of the waves. So the upper portions are the peaks, the lower portions are the troughs. The distance between repeating portions of a wave is called the wavelength, which would give the Greek letter lambda. That's measured in meters. The amplitude, which we generally don't have as a variable, is how far a wave displaces the material up or down. So waves are vibrations through space and time. So something that wiggles, but the displacement goes side to side. So the object may move up, the wave propagates side to side. So as something moves up and then back down, the ripple translates from one place to another while the material stays in one location. You think of a slinky, hold on, I actually have a slinky. Not lying to you. If you have a slinky like so, and you send some sort of ripple in it, some sort of wave, it's hard to get an actual small wave here, but little ripples, vibrations, the vibration travels side to side, but the slinky doesn't go anywhere, right? So the vibration travels, and that causes an amplitude. Sorry, kind of going off on tangents here. Causes a amplitude from where the object would normally be. Same thing with water. The ripple travels away from where a rock falls in, but the water doesn't go flying out. It's kind of hard to tell or understand that when you don't see where things are going because water's clear and all. But ocean waves are a little bit different because there's a cyclic action going on. But that's what amplitude means. Period and frequency are the next two things to take a look at here. Frequency and period are inverses of each other. They're flip-flops of each other. Frequency is the number of vibrations that occur per unit time. So if you were to count a bunch of waves going by and you look at a stopwatch and say, oh, that took 7 seconds, you could take the number of waves and divide it by the number of seconds that's gone by. That gives you your frequency. It's also, if that number of vibrations is 1, there's only one vibration there, then the time that it takes for that one vibration to happen is by definition the period. So we can say that the frequency is 1 over the period as well. Now the units for frequency are a bit tricky because it's not always listed in a problem, whether it's conceptual or mathematical, that the frequency is 17 hertz. The unit is hertz, which stands for per second or 1 over seconds, but sometimes you get phrases like waves per second. Like it'll say a water wave is being created and there's 4 waves per second. Well, that's the frequency. It's 4 waves per 1 second. You can calculate that out as number of waves or vibrations divided by time. It may say vibrations per second. It may say each second. It's always something per second or each second. That's referencing frequency. Period is the time for one wave or vibration to be made. So it's total time divided by number of vibrations, which happens to be the inverse of frequency. But if the time that you record is for just one vibration, that's the definition of period. It's the time for one vibration. So these two are inverses of each other. Make sure you kind of get that idea down. Always reference back to this per second thing for frequency, but frequency is measured in hertz, period is measured in seconds. Wavelength and wave speed. Wavelength we define as the length for one wave. However, you can also look at it as the sum total distance divided by the full waves that exist in that total distance. So for instance, if I have this little diagram here off to the side, it's barely squeezed in there, it says 10 meters of distance and there's all these waves going on. Well, what's the wavelength? Some people would say, oh, it's 10, easy. No, it's not 10 because there's more than a wave in there. I think, oh, it's 4. It's got to be 4 because there's 1, 2, 3, 4 waves. Now, a wave is a crest and a trough. So in this picture, there's 2 full waves in the picture, in that diagram, sorry. So I would take the 10 meters divided by 2 full waves, and I get a wavelength for a single wave of only 5 meters. Now, generally that's not how we do wavelengths. You're just told what the wavelength is, or you calculate it using the wave speed formula. But either way, this is a method that you can use to figure out what the wavelength is. Wave speed, generally speaking, wave speed is just like any other velocity. It's a distance over a time. As in the Hewitt-Druitt, we could put that as wavelength divided by period. Don't very often use that formula. More commonly, we use wave speed is equal to wavelength times frequency. So let's go ahead and do a couple of example problems here together. The first one I got, I might as well show both of them at the same time. I have the technology. Example 1 says, a speaker makes a bass note that pulses the air 30 times per second. The sound travels in the air at a speed of 340 meters per second. What's the period and frequency of the sound, and what are the wavelengths of the sound waves? So let's go ahead and start identifying things. Anytime we got a number, we got to identify that as something, right? So I've got 30 times per second. There's our little keywords, per second. It's not saying it's 30 seconds. It's not saying a wave takes 30 seconds, like 1001, 1002. It doesn't take 30 seconds to make a wave. It's making 30 of them per second. So 30 times per second waves are being made from that bass speaker. If you watch a big subwoofer, you can see the subwoofer vibrate back and forth. That's what it's doing. Every time it moves out and in, it's making a pulse in the air. It's making waves in the air. So this one's doing 30 times per second. We need to identify that. What is that number? In this case, because it says per second, that means it's the frequency. So frequency is equal to 30 hertz. Now, part A is asking what's the period and the frequency. Well, check. We just got the frequency. We're done with that. But now we need the period. So period is equal to 1 over the frequency, or total amount of time divided by total number of waves. It's easier to do it this way and say that it's 1 over 30, and 1 over 30, oh geez, I forgot this in my head. 1 over 30 is 0.033 seconds. So if I'm going to make 30 waves in a second, each wave is not going to take very long. And 0.033 seconds, that's quicker than you can turn on and off a stopwatch. So it's taking that long to make one wave, which means you can make 30 of them in a second. The last step is, what is the wavelength of the sound? Well, they tell us that the wave speed, it's the second number that's given to us. They tell us that the wave speed is 340. And we're looking for lambda, that little upside down y. I always like to think of it as an upside down lowercase y. So that's our question mark, and the formula we would have is v is equal to lambda times f. So let's go ahead and pop in the numbers and do a little calculation. We've got 340 is equal to lambda times 30, and so if we solve for lambda, we have 340 over 30, which equals some number. What is it? 11.33. So the distance from crest to crest for these bass notes is 11.33 meters. That's big, all right? That's 35 feet roughly. So if you've got a bass in a small compact room, it's gonna go all crazy all over the place. But that's also tends to be, there's a couple different reasons for it, but also tends to be why bass travels really well when you're in a big open field. If you go to a concert or something like that, you can hear the bass like from far away. It's because it's big, long waves, and they can expand out, and they're less likely to reflect off of things. They tend to kind of go around and smush about. Big waves. Let's go to number 2 here, example number 2. Sorry, going off on tangents here. It says a tourist at Huntington Beach Pier, this must be pre-lockdown, Huntington Beach Pier notices that they can watch wave crests pass by them every 12 seconds. They also estimate the waves are 20 meters apart. What's the wave frequency and what is the wave speed? So this person, if I kind of draw in what they're looking at, they're seeing waves like this, and they're noticing that a wave crest passes them every 12 seconds. So if this crest right here, the red dot, is underneath them, and they start a stopwatch, the next wave crest wouldn't get there for 12 seconds. So that's the time it takes for a single wave. That's the period. So for part A, we're going to need to calculate frequency, but we know the period is now 12 seconds. Now, for those people that surf, the period of a swell, or the period that it takes for waves to repeat, is kind of a big thing. Short period swells means the waves are really close together and choppy. So I'm trying to get, there we go, it wasn't popping up on the screen. Long period swells tend to mean that the waves are going to be bigger and farther apart, and so there's more time in between them. Long period swells are important. So we can calculate what the frequency is from that. So for part A, we'd have frequency is equal to 1 over the period of 12 seconds. 1/12 is some number I can't think of in the top of my head. 0.0833. Oops, not seconds, sorry. Hertz. It's 1 over seconds. 1 over 12 seconds would be per second, that's hertz. So there's very few waves per second there. It's like a fraction of a wave per second. So 1 second goes by, you're barely seeing a chunk of a wave because they're moving so slow. The next bit is what's the wave speed? Well, we took care of one of those units, those numbers is the 12 seconds. What about the 20 meters? That's saying this distance right here, that's a wavelength. So lambda is equal to 20 meters in this problem. So if I've got a lambda of 20 meters and I've got a frequency that I've calculated, I can calculate wave speed is lambda times frequency. 20 meters times 0.0833 hertz, and that's going to give me a number. I don't know what it is though. It's 1.666666. Right? Yeah. So 1.67. Double check my numbers. Thought I typed something in wrong. So waves are going about 1.67 meters per second. Not too fast. You can run and actually follow the waves. If next time you actually get a chance to go to the pier, Huntington Beach or Seal Beach even, then you can kind of go far out and you can, I kind of made up these numbers, but they're relatively this sort of speed. If you can go out there and when you see a ripple coming in, try walking along with it. It's going to go faster than you can walk, but you can actually keep up with it. It's kind of a fun thing to do if you got nothing better. Anyways, that's a little review of these notes that we post on waves, so you should be able to hopefully apply some of this to those wave problems and do good on them.